So here's a problem that we have. The average waiting time for a patient at an El Paso physician's office is just over 29 minutes, well above the national average of 21 minutes. In fact, El Paso has the longest physician's office waiting times in the United States. In order to address the issue of long patient wait times, some physicians' offices are using wait tracking systems to notify patients of expected wait times. Patients can adjust their arrival times based on this information and spend less time in waiting rooms. The following data show wait times in minutes for a sample of patients at offices that do not have an office tracking system, and wait times for a sample of patients at offices with an office tracking system. So here's what we have. So without tracking, we have 10 values in each case, and these are two independent samples. People who come out of a system where there's no tracking versus one which there's tracking. And so given the data, we ask, like, what is the mean and the median? We could find variances, coefficient of variation. Do we have any extreme values and so forth? So I'm just going to use this data to kind of demonstrate all the things that we were talking about. The very first thing to do with this data, of course, is to order it, because if we want to find things like the median, if we want to identify the mode, if we want to identify quartiles, it would make sense to have the data ordered. And so I've gone ahead and sort of pre-ordered the data and have used a stem and leaf plot, of course, for that purpose. So we could see that this is the unordered plot for the data set without a tracking system, the first one. And then I ordered the plot over here. And then, of course, with a tracking system, we have the stem and leaf plot, and here it is ordered. Okay. So now that we have that, we could go and find the mean and the median and the mode and so forth. Well, in this very first case, actually none of the values are repeated, so we don't have any modes. In the second case, however, I think we could identify a mode of 12 right here. So we at least have two values that are repeated, and so the mode for patient wait times will be 12 in this case. Okay. So now let us look at calculating the medians for each of this data. Because n is 10, so the rule says that if we have an even number of values, that we need to take the two middle values. In other words, if we took 50%, which is the median, 50% of 10 gives us 5, then we must average the fifth and sixth values, because when I, the location, falls on an even value, or sorry, an integer, then we must average the two middle values. So in this case, since we're talking about 10 multiplied by 0.5 gives us 5. And so we would go for the very first case without wait times. We have 1, 2, 3, 4, 5, and the sixth value. So our median should be in between those two values right here. So the median would be 23.5 minutes. For this case, median 23.5. That's in between 23 and 24. I don't think we need to actually add those and divide by 2. I think everybody could appreciate that. And here, the same thing, we got to go between, since we have 10 values as well. So for the case with tracking systems, we count 5 and 6. 1, 2, 3, 4, 5, 6. So we are between those two values. So between 13 and 14, the value that is between there will give us a median of 13.5. 13.5. All right, so that just gives us the median values. But let's calculate and I've already identified the mode as 12. Let's calculate the mean. Mean is fairly straightforward. So we're going to, so the mean if we take, so here's what I like to do is I would take the values and create a table. So I would say without tracking, with tracking. And then I would actually look at my sample size, my sum of my x's, my sum of my x squareds, because I know I'm going to need that for standard deviation calculations. I could get my SSX, right? And then I could get variance if I want to. So S, standard deviation. And then I could get variance, which is just the square of the standard deviation. So it's nice to kind of, oops, crazy. It's nice to create a nice little table that could put things together first with some sort of structure. Well, we know we have 10 in each, so that's easy, 10. What are the sum of the values? So all you have to do is to just add them all up. So the sum of the values will give you 291 without, and will give you 172. Right? So I think that's straightforward in terms of how we add those values. If we go back to the data, we simply need to add the values in the stem and leaf plots. Right? Some of the x squareds, and we must be very careful that we do that correctly. So, for example, for without, the sum of the x squareds would be 2 squared plus 6 squared, 2 squared plus 6 squared plus 7 squared plus 0, so not 2. 12 squared plus 16 squared plus 17 squared plus 20 squared plus, okay? So that's what we need to do with each of these values, squaring each and every one of them. Actually, what I usually do, I just put in a spreadsheet in Excel and I do my calculations that way. It makes life a whole lot easier for us. So the sum of the x squareds after you finish that should be the following. 10,949. So 10,949. And the other one should be 3,734. 3,734. We already begin to see a big difference between those. First of all, some of the values are different. And then some of the squared values are also different. All right, so now to calculate, what we need to do is to find SSX. And remember we said SSX for each case would just be the following. So let me just write SSX is the sum of x squared minus sum of x all squared over n. So in the case without, that value would be calculated as follows. So 10949 minus 291 squared over 10. That's my SSX value right there. And that SSX is 2480.9. You could kind of compute that. 2480.9. If we repeat that for the second one, we'll get an SSX of 775.6. 775.6. All right. So to get the standard deviation of the variances, all we have to do is to divide by n minus 1. So if I divide this by 10 minus 1, that now gives me s squared. So s squared is SSX. SSX over n minus 1. And we know that SSX was 2480.9. 2480.9. If we divide that by 10 minus 1, then we will get our variance. It turns out that that is 275.66. And to get a standard deviation, all we need is the square root of that, which is 16.60. So if we take the square root of this value, you will get 16.60. To get the variance of the times with tracking systems, we do exactly the same thing. We take SSX, which is this value, divided by n minus 1, which is 9. When we divide that by 9, that will give us our variance, which is 86.18. And if we take the square root of 86.18, we get the standard deviation, which gives us 9.28. So here we have mean, we have, where's the sample mean? I didn't calculate the sample mean. Oh, that's terrible. Well, that should be easy. If I put x bar in between here, because I have some space here, then x bar would just be the sum of the x's over n, so that's 29.1 and 17.2. So right away, we have a couple of measures that are useful. We could see here that the average wait times for offices without tracking systems is significantly higher, by almost 12 minutes, than those offices with tracking systems. One of the things that I didn't do, now if we look at the standard deviations, it suggests that the standard deviation is much higher for the case without tracking systems. We could calculate the coefficient of variation by taking, and remember we said that is S over mu, so we would have to take the 16.6 and divide it by 29.1. So that's 16.6 divided by 29.1, and we would have over here 9.28 divided by 17.2. All right, so those values would give us the coefficient of variation. And let me see if I could just calculate that very quickly. This is equal to, so I'm doing a calculation here on my spreadsheet. Okay, so actually, interestingly enough, the relative variance is quite close. It turns out that when you do that calculation, if you have a calculator, you could have done it a lot faster than I did. Then it turns out that it is 0.57 over here and 0.54 over here. So we still have a reasonable amount of variability in both cases, but it is slightly smaller. The relative variation is slightly smaller in the cases where you have tracking systems versus the ones when you don't have tracking systems. All right, so that gives us quite a bit of data. That we have coefficient of variation, we have variance, standard deviation, the mean. We calculated the medians as well, which we could have added to our table, and we found medians of, if I go back to my earlier slides, of 23.5 and 13.5, 23.5 and 13.5. So we could certainly add those if we want to. Median 23.5 and 13.5. Now if we look at the mean overhead, the median, sorry, which is 23.5, and the mean, so it tells you that you see that those two are not identical. The median is smaller than the mean. The mean is larger. So there must be something that sort of pulled it up a little bit. And if you go back to our stem and leaf plots, you see here that that value of 67 kind of was a large value relative to some of the other values. So that sort of pulled the average up a little bit. And I believe, let's see what we have in the second case here, where the median is 13.5, but the mean is 17.2. Same idea, that there are a couple of values that probably pulled the mean upwards. And if we look here, you have 31 and 37, while most of the values are in the teens down here. All right. So that tells you that we have we're slightly skewed to the right with both of these data sets. And it can be seen by just drawing the graph. Sorry, right here. So slightly skewed to the right. Skewness of the second one is actually a little less than the first one. Nonetheless, we do have some skewness. Let's see what other questions we had there. So we had to find the variance, standard deviation. We found that the mean and the medians. We found that we could find quartiles if we wanted to. Actually, we didn't find a range. We certainly can find a range by simply taking the smallest value from the largest value. So in this case of without tracking systems, 67 is the largest value. 12 is the smallest value. So the range in this case would be 67 minus 12. So R for without 67 minus 12, and that gives us 55. R for with, smallest value is 9, largest value is 37. 37 minus 9, and that gives us 28. So you could see a smaller range here compared to the 55 in the other case. And then if we actually found the first and third quartiles, we could get the interquartile range. The data set is fairly small. I'm not sure we actually need to do that much evaluation. Okay. The last thing that we might want to do is, I think we will ask the question whether or not we had some outliers. Let me just double check that. Do offices with a weight tracking system have shorter weight patient times than offices without? Clearly, when you look at that, the answer is yes. And what's the reason for that? Well, the reason for that is information helps patients make a decision that would allow them to come slightly closer to the time that their service ought to be delivered. And so as a result of that, you have a natural effect. It's kind of like even when you are placed on hold and you're told that this call will take approximately 10 minutes. But if you hang up immediately, people who would find that the waiting time is too long would actually hang up. So if you actually look at data on how long people waited, folks who would have, if everybody stayed in the queue, then you would have had one set of results. But if people who felt like they would have waited too long decide to leave the queue, then you're only left with people who stayed because the wait times are going to be short. So therefore, you have a bias that shows that the wait times are smaller. Okay, so I think you have a similar situation that people will self-select. If the wait time is going to be too long, they're probably not going to show up. But so they decide to go based on whether or not they're willing to wait that much time. And well, I mean, there are other factors too. Of course, the severity of the situation that brings you to the doctor. You might actually go in irrespective of how long you have to wait. So that's something to keep in mind. So that's how we would actually work with this particular question, which is fairly straightforward. Okay. I want to do a second question and just oh, actually, I'm sorry, I should just mention that we could calculate the z-scores because now that we have standard deviation, and if I go back here, we have the standard deviations. We also have the means. We could calculate z-scores. And remember what a z-score is. A z-score is just simply the distance between an observation and the mean expressed in standard deviations. So let's do one calculation so that we can see what we're talking about. So if I were to take that 67 for without, 67. So the z-score for 67 would be 67 minus 29.1 divided by the standard deviation, which is 16.60. That's all. That's all there is to it. And so when you do that computation, you should get a z value, and I don't have my calculator with me, so I'm going to cheat a little bit. That z-score turns out to be, if it's, I believe that this is the data when it's not ordered. So the 67, I think, is the one that gives us the highest z-score. And so that's that 2.28 that you will see here. All right. And remember, we had a rule that says we consider a value to be an outlier if the z-score is higher than +3 or lower than -3. So in that case, I think that we're okay. We have no real outliers in this data and no outliers in this data right here. All right? So that brings us to the end of that question.